So good afternoon, everyone, and welcome to this joint webinar organized by the IABSE Italian and German National Group. This is the second of two webinars dedicated to the analysis of the Carolabrücke collapse. My name is G.Fanigliulo from Studio di Ingegneria delle Strutture, and I'm the Italian chair for the IABSE Young Engineers Program, and I'm a member of the YEC board. Today, together with my colleague Francesca Lomurno from TechnSPA, I will have the pleasure of moderating the session. So I'll hand over to Francesco, who will share a brief recap of our last session.
Yeah, thank you, Giovanni. As this is the second appointment. In the previous webinar, we had the pleasure to listen to interesting presentation. The first entitled Technical Analysis of Carolabrücke Collapse by Gregor Schaft. And the second was Corrosion Mechanism and New Findings by Gino Abel. Two interesting presentation which deal with mechanical causes of the collapse and detailing studies about the corruption. Now me and Giovanni will after we will introduce the speakers and manage the part of QA session. And now I leave the floor to Nadia for the presentation of IABSE Italy National Group.
Thank you, Francesco. Good afternoon and welcome to everyone also for me. Now, before starting, I will try to share a brief introduction of IABSE. Before starting, a couple of information about this webinar. This webinar will be recorded and then posted in the learning web page of IABSE. Then, as anticipated by Francesco, you can submit your question during the presentation using the Q&A button on the bottom side of your screen. And then we will have a brief discussion at the end of both presentations. So I try to start a brief introduction. Okay. So, two words to remember who IABSE is and what it does. IABSE is an organization of engineers with a mission to exchange knowledge and advance the practice of structural engineering worldwide. IABSE is interested to all the aspects in structural engineering, all type of structures, not only limited to the bridges, and obviously also all the aspects related to the construction process. If you are not yet a member of IABSE, you can become part of this great organization as an individual or collective member. We have our members all around the world, more than 100 countries, and for this reason we have several national groups that are very active to organize webinars and conferences. In Italy, we have also a national group, IABSE IT. It was refounded recently in 2022, and we are trying to promoting several activities related to technical task groups, dissemination activities, and training activity also. Upcoming conferences, we will have the next IABSE Congress in Incheon in Korea. I would remember to you that the early bird registration has been extended up to 19th of July. Looking at the next year, we will have the IABSE Spring Symposium in Guayati. And then we are proud to announce that the next IABSE Congress will be held in Italy, hosted by the University Politecnico of Milano. The call for abstract is already open, and the deadline is for mid of September. So I invite you to send your abstract, as we have a lot of general and special sessions, so I'm sure that you can find a proper topic for your abstract. Webinars are obviously free for all. You can find in the learning page of IABSE the past webinars. And I would bring to your attention two upcoming webinars. The first is related to seismic response control, organized by Philippines and Japanese national group. And the second is focused on Wang Maoai link, organized by the Chinese national group. So I'm honored to give the floor to the secretary of the German national group, Mr. Peter Seitz. Please, the floor is yours.
Thank you, Nadia, for introducing the IABSE organization and the activities of the Italian group. I'm the secretary from the German group, and I wish a very warm good afternoon from our chair, Professor Siebert, who is he's currently in the US and cannot attend due to the time shift. So the German group is also very active, and we organize the Young Engineers Colloquium, and this time this will happen in September in Stuttgart. So if you're interested in attending or handing in a presentation, presentations are still open till 15th of July, and you can see more about more information about it on iabse.de. So I think those who have already attended last week's seminar are very keen on having new insights on this topic from this collapse, and I hand the floor to Giovanni to introduce the speakers, and we are looking forward on this webinar now. Thank you.
Thank you, Peter. So I'll briefly introduce today's program. So first, Francesca Buttarazzi and Giorgia Di Benedetto from Autostrade per l'Italia will present their company's experience with existing prestressed concrete bridges. And afterwards, we will have a presentation by Max Fiedler from Marx Krontal partner about acoustic emissions monitoring of prestressed concrete bridges. Just like Nadia and Francesco said before, at the end of the presentations, we'll have a discussion and a Q&A session. So Francesca and Giorgia, the floor is yours. Let's start.
Thank you. Thank you. Good morning. Good afternoon, everyone. First of all, I would like to thank Nadia Zoratto and the IABSE organizing team for the invitation and for giving us the opportunity to share our experience today. I'm Francesca Buttarazzi. I am the technical director of the structural department of Tecne, that is the engineering firm of the Autostrade per l'Italia group. My activities mainly focus on existing bridges as well as the design of new infrastructures, but today we deal with the assessment, monitoring, management of existing bridges. Before starting, I would also like to acknowledge the contribution of many colleagues that are working on this topic over the few last years, and especially Giorgia De Benedetti, that she's here with me, and Roberto Crapanzano and other colleagues that work with us on this topic, also about Autostrade per l'Italia. I hope our experience can give you insights, useful insights to infrastructure managers as well as the engineers that deal with this topic and with these problems and challenges in the network every day. So after this brief introduction, I will share my screen with the presentation. I hope everything is working. Let me see. Share. Okay. Yes. Wait a minute. Nothing. Yes. Okay. 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 Now it's working. And in this way, okay. Okay. ASPI network post-tensioning systems, assessment and management. Why we talk about the management issue of post-tensioning bridges? As I think we all know, post-tensioning concrete bridges represent a significant portion of the motorway infrastructure built during the second half of the 20th century, especially between 60s and 90s. And especially in the period of 60s and 70s, we know that these structures were built without regulatory really known about how to do this structure, even if the technology was being experimented in that years and even before. But the problem is that even if these structures have generally performed well during the time, some of the most critical deterioration mechanisms can develop internally, as we have seen with the Carola bridge in the past, beyond the reach of conventional visual inspections. So this raises to a fundamental asset management question. How can a motorway operator detect invisible internal defects before they become critical? And if you see the distribution of our bridges of, can you see the charts? No, you don't see the charts? No. Wait a minute, I will, sorry. Let's, perché ora sto, sorry. Perhaps is that now? Okay.
Yes.
Okay, let's do like that. Okay. So the question was, how can a motorway operator detect invisible internal defects before they become critical? And if you see the distribution of our bridges, you can understand that this is a very critical question for us, and we have to respond in an organized way. To understand the problems is also important to understand the scale of the problem. Here you have some numbers about Autostrade per l'Italia network, especially you see we have more than 2,000 bridges with a length over 10 meters, more than 2,000 overpasses. And you see that the size and diversity of the network mean that special inspections can be planned as isolated actions. So we have to answer to many questions: which structures first, which guide, which cable, which samples, which techniques. And so this is why the answer has been an organized process that, starting from visual inspection, transforms the data collected during visual inspections into engineering decision and a management strategy. To do this, we have to follow this chain of actions: the prioritization, the definition of the samplings, the diagnostics, and then we can define the proper strategy to manage the structure. As you see, all this step is in some way defined by some guidelines. We are working on that, even with the regulatory, with our Ministry of Transports, as well as some consortium of universities. You see here the Fabri protocol, but first of all, the bridges guidelines that were issued by the ministry in order to adopt a multi-level, multi-risk framework for bridge asset management. But then you see that the single manager has also the necessity to do some internal document, such as the one of prioritization, or also the one for technical regulations, in order to provide technical operational guidance on the various phases because we are, it's not only the same laboratory that is on the field, it's not only the same engineer, of course, that does the inspection. So it's important that the activities is done following the same regulations in order to have also results that are comparable. The general framework, I want just to give you a brief note to the Italian bridge framework, the Italian bridge guidelines that has introduced this general framework to manage existing bridges. This was this flowchart has been translated. Of course, it's in Italian, but you have the reference of an article in which you can find all the description of this flowchart, and you see that the objective of this flowchart is to have an organized sequence of activities that has the objective to define the interventions, the bridges in which you have to do interventions, but at the same time, with all these activities that start from the census to the inspection and then to the classification of risk and the preliminary and accurate assessment, the objective is to reduce the risk of the network, as well as doing the priority to the managers to assess all the bridges of their portfolio. So now we will go through the process I have shown you before, starting from visual inspections that are, in any case, the first step you have to do, because we have to look for warning signs. And these warning signs can be visible defects as well as warning defects. In Italy, there is even the bridge guidelines or the Fabri document have introduced this differentiation between defects that are evident. So you see cracks, you see the reduction of prestressing reinforcement, you know that there is something that is not going well on that structure, but there are also warning defects. So these are defects that does not reveal the full cable condition, but they can help the engineer to identify attention zone for the following investigation. After we have done the inspection, we have all the data to do the prioritization. Of course, we also use the data collected in the level 0 phase, so in the census. And here we have we have defined in accordance with the Federal Highway Guidelines, priority index, that is a combination of the probability indicator of damage and a collapse consequence indicator. So as well for risk analysis, we have also something that is connected with exposure and something that is connected with vulnerability. And here we have used the weight that are defined in the Federal Highway Guidelines. In some case, we have done some adjustment for the Italian situation and also for the IABSE management needs. And as you can see in the distribution, the indicator runs from 1 to 25, but you see that there is a distribution like a bell, I think it's clear. And here we can have the opportunity to put in order our structure and to decide on which we go first. After the selection of the bridges, we have another question, what we have to investigate. And here we are following a statistical-based approach that is the one introduced and first introduced by the Federal Highway document. I have already said, I have already remembered, and in this case we have to do some assumptions because we have to define the acceptable percentage of cables with defects. This is something that we assess at the beginning, and then we can decide after the first phase of inspections if we have to change our hypothesis at the beginning. In any case, we start generally with a 20% acceptable cables, and then defects, sorry, and then we define the total number of cables in function of the number of beams and the cables number. And for every cable, you see also the critical zones in which we have to do the inspection. So the mid span, the area affected by percolation, but also the anchorage zones that are generally the ones that are more affected to have defects. What we do now, after we have chosen the structure and we have decided the sampling and where to do the inspections, we follow an organized sequence of actions, of activities that are is the localization first with the georadar and geometric reconstruction of the PT system in order to localize ducts and cables layout before intrusive actions. Then we have the phase of defect screening. It's something that I will show you some results later. We do this with ultrasonic tomography. And in this is useful because we can identify potential voids or anomalous zones without destroy the beam. And then we have the confirmation. In some cases, is generally we do every time endoscopy, local openings, micro demolitions in order to go deeper into the defects and also to measure the corrosion, the lack of grout, and also the grout condition. So here our idea is no single technique solves the problem. Reliability comes from sequencing techniques and interpreting the results together. It's important to follow this sequence of actions in order to have then the possibility to give the right answer. And now I want to brief touch on the different techniques. I know that these are well-known notes, but I think it's interesting to have our results from our in-field activities. For example, for the GPR technology that is used to determine the construction, it is details. It is very important to set the frequency according to the depth of the object of investigation. Then sometimes it's also important to do some destructive tests in order to supplement the data acquisition. And it's important, the georadar, because sometimes we don't have the correspondence between the drawings, the as-built drawings of the bridge and what we find in the field. And especially for the cables that are placed in the slab, sometimes we find some surprises on field, and that are the cables that are frequently affected by defects. Tomography testing is also, as I have said, a method, a technique that we always use in order to identify potentially anomalous zones. These results can be interpreted in relative terms, sorry for this interruption, and attention areas must be subjected to direct testing. Our experience is that generally in the 50% of the anomalous zones, we then find also a defect. So there are some false negative false positive that have to be checked with direct inspection. Just to mention that the tests are not effective if fiber reinforced concrete and beton plaqué are present, and it is important to not position tomography acquisition station at the mid-span introdos of the beam or along the lateral surfaces of the slabs. Here is the techniques that I like the most, because here you can see, you can go and see and you can measure, but in this case also we have a different approach. We start with endoscopy inspection, so very local inspection that must be performed carefully to avoid damaging the cable. And then if we find some defects, we go with local opening wide enough to expose at least semi-diameter of the cable. And there you have also the possibility to measure what, for example, you can see in this picture. So measure the reduction of the diameter. And in this case, you can have, these are all the information you need for the following evaluation of the structure. In some cases, we are also experimented some digital X-ray radiography used to obtain high-resolution images of post-tension cables. In these years, there have been developed low-power instruments that are compliant with the provision of legislative decree. And as you can see here, it's very interesting because with this digital ray, you can really see the cable, the absence of grout, and in case you have the defects, you see the defects. For example, in this case, grouting defects you see here. These are some pictures that show the potential of this activity, of this technique. What I want to say is this is a technique that cannot be used on a large scale, but must be selected for specific case. And with this, we go also to another, I'm really sorry. Sometimes it's not sufficient to do local testing, but we have to do to a global understanding of the structure. In this case, we use load testing or dynamic testing. We are aware of the difficulties to use this testing to identify defects or something that is crack patterns or something like that, because they are not testing that can be used to do that. But for sure, they can be used to assess the global stiffness, the integrity of the structure, but even how the joints of the structure are behaving and how they affect the behavior of the total structure. And these testing are also important because in some situation we have to follow. Sorry, I have. We have to follow after the inspection, the single inspection. We have also the possibility to install some monitoring in order to follow the structure with time, especially if we have some deformation to monitor, crack displacement, something that is connected with the environment parameters. And for example, also the acoustic emission strategy or techniques that will be, that is the topic of the next presentation, is something that can be installed and used also for a monitoring action activity on the structure. Before wrapping up and going to the conclusion, I want to also show you a case study of the IABSE network. This is a very long bridge, more than 1 kilometer long. That is the 0.4% of the structures of the IABSE network. So it's a particular structure, and here we have a lot of beams, a lot of and also many cables, of course. And we have followed all the process for investigate this bridge. And starting from an historic analysis of all the data that were collected in the past, it's important to say that it's not only in this year that we are doing these techniques, but it's clear that now we have an organized approach that wasn't available before the issue of the guidelines, the bridge guidelines in Italy. We have started with visual inspection, detecting 86 warning defects and 3 visible defects. Then we go to the strategy of sampling, defining the critical spans to be selected and investigated, and the cables to be selected. And then the diagnostics. In this case, you see that we have done 400 tomography. Of this 400 tomography, more or less the half of that give us some anomalies. And in this case, the percentage of positive results from the anomalies was a little less than the 50% I said before, but we have found 28 missing routes and 12 corroded wires. In any case, the important is that with this investigation, we have the opportunity to understand that the cables that were anchored in the slabs were the ones that are more affected by defects. And so now we are in the strategy moment. We are defining our monitoring and maintenance planning. Of course, we have made also some partial traffic restriction because we have done also the assessment with the level 4 evaluation of destruction, defining the reliability of destruction. And this is a case in which the chain transforms inspection findings into engineering decision, allowing hidden defects to be identified, assessed, and managed through a structured asset management process. I want also, before going to the conclusion, give a focus and it's also highlight the importance of archiving all the data we are collecting. We have an Annex D that is the one that is required by the bridge guidelines. So it's a report we have to do with all the data we collect, but then ASPI, Autostrade per l'Italia, is working also on a digital archive in the Argo platform in order to have all the information connected to the beam element of the structure, and so you can check before going on site if you have done already some investigation and what you have also, and if you have to do some assessment, you have all the data collected. This is a work that that has a great potential even for the use of AE technologies, and I think also for the recognition of defects in order to optimize our activity on site. So let me conclude with some few messages I want to give you. As I said at the beginning, hidden cable defects are a major management challenge for aging prestressed concrete bridges. Visual inspections are necessary but not sufficient. They must be integrated with targeted diagnostic campaigns. Periodization transforms a large asset portfolio into a rational inspection program. The fabric-based progressive approach supports the selection of samples, the location of the investigation, the choice of the test types. As we have seen, no single technique is sufficient. Effective diagnosis requires a sequence of complementary methods, and interpretation is as important as measurement. Monitoring and formal reporting turn observations into decisions and allow continuous improvement of the system. Knowledge must be structured and traceable. Inspection and testing data must be systematically collected and stored. So to answer to the question we have put in the first slide, invisible defects become detectable when inspection, diagnostics, monitoring, and engineering expertise work together within a structured asset management framework. Thanks for the attention, and sorry for some disturbance during the presentation.
Thank you for the incredibly interesting presentation. We'll now quickly move over to acoustic emissions monitoring for prestressed concrete bridges with Max Fiedler from the Marx Krontal partner, and eventually with the Q&A session. Thank you.
All right. Thank you then for having me too, and a good evening to all of you. I hope you can now see my slides and I can start with the presentation. So I'm very pleased that you have me for this talk on acoustic emission monitoring on prestressed concrete bridges, which is a topic that follows me for almost 10 years now in the company of MKP. We started our first project almost 10 years ago. In 2016, we installed the first bridge with an acoustic monitoring system. even though, and that is something that we have to say, it's not a new technology at all if we think about it in which applications. Or already in the 90s, there have been first applications of acoustic emission monitoring for wire break detection specifically. But yeah, after a long time of quiet, so to say, this technology arose, and I think it specifically arose in the last 2 years, especially in Germany due to the collapse of the Carola bridge. And yeah, what we can do with this technology, I think this is something that you might have already heard, is that we can listen into the structure, that we can detect the damage occurring within the tendons, within the pre-stressing wires that are suffering from stress corrosion cracking. And stress corrosion cracking is something, I think Gregor already explained it in the last session, is something that mostly starts evolving during the construction phase, and during the service lifetime it's more sort of a fatigue issue, and so these wire breaks can occur over the lifetime of the bridge. And so whenever we listen into the structure, and whenever we have to assume that the damage occurring inside the structure is not propagating, so to say, in form of cracks to the surface of the structure, we are not really able to detect this damage unless we apply acoustic emission and listen to the structure, and then we are able to identify critical areas, and then we are able to assess these structures with this technology. In general, and this is something Francesca already explained too, for the assessment of such bridges, we are not only using monitoring or acoustic emission, but we also apply computational assessment, these experimental investigation like diagnostic methods, also regular inspection, visual inspections, and all the four in the end make a good assessment. So monitoring is only one part of it, and especially acoustic emission is only one part of it, but it complements all these methods, all these especially existing methods like computational assessments, in terms of continuity and immediacy. Because what we are able to do with acoustic emission is that when we listen to the structure, we are almost in time getting a message, an alarm, if a potential wire break occurred, and we are then able to react to this alarms. So what's behind acoustic emission? What does it mean? So the basic principle is that elastically stored energy within a pre-stressing wire, when the wire breaks, this energy is released, and then the energy can propagate within the structure as an elastic wave. And wherever we have applied a sensor to the surface, and whenever this wavefront comes to the surface, we are able to detect this wavefront and to detect this energy within this wavefront. And when we talk about acoustic emission, we always have to take into account the propagation path the signal already traveled. So with longer propagation paths, the signals suffers from attenuation, from scattering. And so this is something we have to take into account when we analyze signals from acoustic emission sensors, but also the other way around. When we design a sensor layout, we also have to take into account this attenuation and also the intensity, the possible intensity of the source signal, which in this case is the wire break. So this is something that we have to be always aware when we apply such monitoring systems. Sensors distances cannot be like exorbitant long. They have to be within a specific dimension. Otherwise, we are not able to detect all wire breaks potentially. Due to this is a very complex method, and due to this is also going along with a lot of things that you can do wrong. In Germany, we released a guideline together with Stefan Piskowitz, for example, from the BAM, from the Federal Administration Service, together with the German Society of Non-Destructive Testing. And within this guideline, these fundamentals and possibilities, limitations of this methodology are explained, regulated, and the requirements for this measurement technology are described. And yeah, there are some examples on sensor arrangement on the structure, and the structure content is described, and also the qualification bidders in terms of a tender project are explained. And this is maybe interesting for the international community. This guideline is in translation. I think there's sort of the last review right now. So whenever you are interested, I think it's going to be released within maybe next half year or something internationally too. So I think there you have a good basis for applying this methodology. And the application of acoustic emission sensors, like from a measurement perspective, is one thing. So meaning that you choose the right sensor, choose the right data acquisition properties, and are able to detect these signals. But what is actually the more interesting part is, what do you do when you measure wire breaks or potential wire breaks, and you assess them as confirmed wire breaks? Because then you have to think about the structure, then you have to think about the load bearing capacities the structure potentially still has. And we at MKP developed a assessment strategy that divides here into locally correlated events and locally distributed events. So what we can do with acoustic emission is that we can localize the events, so where they occur and when they occur. So we get information on the local distribution, on the spatial distribution, and the timely distribution. And this allows us for a very specific assessment in this time. And we combine this with the regulations we have in Germany for assessing structures endangered to stress corrosion cracking, and from there derive these alarm values, so to say, for locally correlated events and locally distributed events. I think if I go into detail with this, we can talk more than half an hour here, but I would just want to inform you about that, because what I want to do now is to spend you the rest of the talk with three examples. First of all, of course, I want to show you how we applied acoustic emission in the case of the Carola bridge, because this is what it's about here. And then I also want to show you some examples from some other bridges that we worked on in the last year, which are very, very interesting, I guess. So when we speak about the Carola bridge, I think you remember that at some point, the demolition of the superstructure C, which was the one that collapsed, the demolition and was progressing, and at some point the River Elbe was about to be set free again, so to say. And the River Elbe is a federal estate for traffic transport on the rivers. And this is not used by Germany very much, but by the Czech Republic. And the Czech Republic had a very high interest in transportation of high load freights on the River Elbe. And so the remaining superstructures needed to be assessed in terms of their remaining load bearing capacity. And as we found also damages of endangered of wire breaks there was obviously the question, how are these superstructures still, do they have enough load bearing capacity? And this is when the city of Dresden decided to monitor these sections, the red section of the superstructure, with acoustic emission monitoring. And this decision was made somewhere around mid-December 24. And here you can see the sensor layout. So we only focused on the section between the pillar 3 and pillar D, following the tendon line, and focusing also specifically on the road plate above the pillars, especially in the axis D, because there we had the most damage detected from the diagnostics. And this monitoring concept was then implemented within, let's say it was 4 weeks, so to say. By the 2nd, 3rd of January, the technique was installed. And then we decided to have a preliminary monitoring period, so where we just wanted to observe what's happening within the bridge before we allowed some ships passages to happen. And as it always is, when you have such a period, within this period, you can see it here, some signals, so over time, and some acoustic emission feature, which is a peak amplitude on the y-axis. And within this period, we had nearly no serious acoustic emission. Some came from diagnostic work, some came from electromagnetic coupling because of the electricity inside the bridge, because the switches went on and off. But nothing really severe and nothing really specific. And just from the day, so on the Monday, the 17th of February, we wanted to start with the ship passages. And as it always has to be, from the night, from Sunday to Monday, the temperatures fall, and then the wire breaks occurred. Or at least we had very high intensive, very high specific characteristic signals detected. And these signals were also localized directly within the plate, directly above the pillar D, sorry, localized there in the superstructure. And so what we did before, when we installed the monitoring system, we tried to guess how many wire breaks we can allow during this monitoring period, and this of the remaining service lifetime. And so we put a traffic load in our model that we had, and we assumed that the bridge before the collapse of the superstructure C, the other superstructures suffered or were able to bear a load of 2 kilonewton per meter, so very light traffic load, and we translated this traffic load into allowable wire breaks, which in case of the pillar D were 14 wire breaks. So by one night from the Sunday to the Monday, we detected several wire breaks within this plate, and so our allowable wire breaks reduced about 1/3. And so there was a lot of trouble within the administration, as you can imagine, and we also were thinking, how can we progress with it? Because with every night we proceed, these allowable number of wire breaks could reduce by a significant step. And so we needed just more time, so to say. And so this is how we then continued, just day by day. We very closely observed the signals coming in and decided day by day what we can do. And so after a further period of observation, by 2 weeks later, we then finally allowed some ships passages, and every time we had no further signals detected, no further events detected that were related to wire breaks, we got more, so to say, sure that this is a good way. And this was very intense for the people within the project, because every day you had to do the decision, can some ships passage happen or not. Another example I want to show you is the Waren-Herrensee Bridge. So Waren is a city in North Germany. And this bridge, you can see, is a roadway bridge passing over a railway line, which is a very important railway line towards northern Germany, and also some other federal roads. And this bridge was constructed with the so-called Hennigsdorfer prestressing steel, which is one prestressing steel endangered to stress corrosion cracking. And during the visual inspection of the superstructure over the railway roads, longitudinal cracks were observed. And this led to the closure of the bridge by the end of 2005. And since this bridge is of high traffic relevance for the city, because otherwise the detours are very long, there was a question, what can we do to maybe recommission this bridge again? So first of all, to assess this damage that was detected on the underside of the superstructure here, on a very short basis, acoustic emission monitoring system was installed, and also some other diagnostic measures was undertaken in this railroad field. And you can see the sensor layout over here. So just focusing on the two neighboring pillars and the railway field. So the installation was done overnight, within one night. And also the diagnostic was done within the same night. So there was a lot of different traffic under the bridge, a lot of people around to gather as much information in as short time as possible. And so this monitoring system then was in operation for almost 3 months, and nothing really happened. So we were pretty sure that we can continue with this bridge on a very good basis. And we developed a diagnostic program where we wanted to do tendon sampling, material sampling on the tendons from the upside of the bridge, from in the pillar areas. And what we found there was a typical formation of these cracks, stress corrosion cracking indication. And also when we opened the tendons, already the first wire break because of the stress redistribution, direct sun on the wires, so different stress situation, and so these wire break spontaneously. And we closed then the tendons, and since we had this monitoring system already installed, we were able to track the progress of damage very specifically in this case. So on the 6th of March, which was a Friday, unfortunately, so to say, and the tendons were already covered with concrete, even more wire breaks occurred spontaneously. And we, as you can see here, so we were able to measure all individual wire breaks. And as you can imagine, when you have such a situation on Friday and it's not stopping, you're getting nervous because at some point this could lead to a collapse of the part, so meaning the bridge is falling on the railway tracks. But what was a bit of a luck is that we had a very narrow network around the pillar, and we could really, with high precision, localize these wire breaks specifically there where we opened the tendons, which means that our manually grabbing into the wire was most likely the impulse for the bridge or for the wire breaks to occur. And this tracking of these unexpectedly induced wire breaks is something that, to my knowledge, was not done before, and which in this case is something very interesting found, because with this knowledge we are able to give information about the assessment of the bridge and about the load bearing capacity remaining of the bridge, because even though we have a damage in this system, we know how much, and know also, because nothing else happened wherever on this bridge, that we can have possibly a future with this bridge in some case. And another example I want to give you is another bridge in Dresden, the Budapest Street Bridge, which was given to us like closely after the Carola Bridge, because obviously the city of Dresden was very nervous about their bridges at that time. And since the designer of the Carola Bridge was the same designer as of the Budapest Bridge, and the Budapest Bridge was a bit younger as the Carola Bridge, everybody was pretty nervous about it. And what you can also see from the top view here is that we are passing a lot of railway lines close to the main station Dresden, which is located over here, and also a very important street in Dresden, the so-called Ammon Street. And so we installed a complete acoustic emission system on this bridge, also another fiber optic system. And the plan was also to do diagnostic investigations on this bridge, just to get a complete assessment, or the foundation for a complete assessment. And from the beginning of the monitoring, we had some really, so to say, suspicious signals. And for a period, we just had a look on the signals and observed the bridge behavior, how it behaved over a certain period of time. And what was very taking our attention is that everything concentrated on one axis, which is here the axis C. As you can see here, the bridge in its longitudinal section here, all the railway roads, and here this Ammannstraße, as I said before. So this axis C got a highlight for us. And so since we were planning the diagnostic measures, we specifically planned to go into this ecstasy. And since we knew from the Carolabrücke and from other investigations that the tendons from the upside, so from the top of the pillar, are the most endangered one, we also went there from the top side into these tendons. And what we guessed from acoustic emission here is that what we found the white spot with the diagnostic investigation, because these tendons over there had severe damages. And what happened after then is pretty clear, because we had a significant number of potential wire breaks there. This section of the bridge got closed, and we could then very specifically for this bridge design a supporting system. So because the road closing was to some from of the Amannstraße was not really an option, so there needed to be some supporting emergency supporting of the Budapest street bridge, and this was designed in there in a very specific manner. So to conclude from this, I think I hope I could show you that the application of acoustic emission delivers a lot of potentials for a very specific assessment of critical structures and also identifying critical structures, because these are 3 examples of critical structures, but we at MKP, we monitor 25 bridges now, and these are some of the few that are very critical. So we can also say for the others, which have shown no critical events, that they can be under traffic for just further decades, so to say. And what it also enables is implementation of very targeted measures, as seen in the last case. And the standardization of in this field made everything more transparent, especially for authorities. And this is something that is very, very helpful for everybody, I think. And it also needs to be highlighted that acoustic emission monitoring is only one component in the assessment strategy for stress corrosion cracking, because you always need to have a recalculation and an escalation concept in cases of damage events or critical cracks showing or whatever. And diagnostic is a very important tool. And also experimental load bearing assessment can be a part, meaning load testing, whenever you talk about recommissioning of bridges. So thank you for your attention.
Thank you, Mr. Fiedler. We will now start the Q&A session with 2 questions from the public. So Mr. Holberg has a question for Georgia. So he asked about, he was interested in the assessment of vulnerability and not necessarily collapse in your assessment process. And he expressed some interest in how the data is acquired for quantitative assessment.
Good morning. I try to answer because Francesca has a commitment, a personal commitment. How many bridge to assessment in the year? We are organized to do a program, and in this year we are check until 20 bridge, 20 structure for the year, for the success in year, probably the same number we try to check. This is the okay.
Right. Thank you, Georgia. Now we'll move on to another question from Mr. Holberg, directed to Mr. Fiedler. So in the case of the Warren Bridge closing, he's asking why this was not a solution, because the breaking of wires continued even without traffic loading.
So what we need to do always is to have the calculation assessment, diagnostic assessment, monitoring assessment, and so on. And from the calculation assessment, the bridge delivered enough load-bearing capacity in our opinion, or after our assessment. So this is the case. And now there's going to be a load testing. So now the bridge is not under traffic, but most likely it's going to be if the load testing delivers successful results.
And we've got another question regarding the costs about this system, the acoustic monitoring system for a bridge with about 20 sensors.
A monitoring system of about 20 sensors, well, that depends on various factors. First of all, how easy can you access a bridge? So especially if you talk about railways situations, at least in Germany, you have to close the railway, you have to apply for closing railway and so on. So just starting working sometimes means spending 100,000 euros. So you have not done nothing but spend a lot of money. And if we talk about the sensor, it's about maybe 2,500 euro per channel, depending on the size of the system, maybe 2,000 euro per channel. That depends on the size of the system and whatever your workers and how fast your workers can work. The rest is accordingly. Yeah, so this can be surprising.
Thank you for your very insightful intervention. I will now give the floor to Nadia, which has another question.
Thank you, Giovanni. I would close with a question for Georgia. You have presented a well-structured work plan to keep your structures under control. So I would like you, which is the progress of this project, this interesting project, and if you have any additional suggestion about monitoring techniques for your bridges that typically are simply supported span with several beams.
Thank you, Nadia, for the questions. This is a long project that start with the visual inspection and continue with diagnostic sampling strategy and so management strategy. The point of end, so the end point is monitoring of structure. When we monitoring support the observation of structural response over time. We can check and we can see the crack, the displacement, and also environment parameters. So from episodic inspection, visual inspection, or diagnostic inspection, we can continue with to know the behavior of the structure. So the future is monitoring and also engineeristic evaluation for our bridge.
Thank you, Georgia. So I think we had a short but interesting discussion about the topics that we have seen with this webinar. Before closing, I would thank, first of all, our attendees for listening to the presentation, our moderators for the organization of these webinars, and I'm grateful to our speakers, engineer Max Fiedler, Francesca Buttarazzi, and Giorgio De Benedetti, for sharing with us their very interesting presentation. So we can close here, and thanks again to all. Bye-bye.